Howdy all, this is Yuvaraj Suresh Babu and I'm here with my teammate Karthigeyan Muralidharan. Today we'll be doing a presentation on the Divas framework, which is focused on automating SOC security analysis and enforcement using LLMs like ChatGPT and Bard. So let me first start by explaining why this framework was even needed in the first place. So today system on chips are incredibly complex. They combine many IPs like crypto engines, memory blocks, DSPs, and all these communicate in a shared bus. These IPs can either be trusted, which is like they're developed in-house, or it can be untrusted, often licensed from a third-party vendor. Now, because of globalization, like from outsourcing and outsourcing of IPs, there is a growing security concern. So we cannot blindly trust every component in a system. This is why zero trust models comes into picture, and it assumes no component is secure by default, and there is a huge shift in mindset. So the real problem is that the SOCs are mostly verified for functionality and not for security. Right now, identifying vulnerabilities depends highly on manual code reviews, audits, static analysis tools, and writing assertions by hand, all of which are tedious, error prone, and are not scalable. So this paper, the author here proposes a framework, Divas framework, that leverages LLM models to automate the entire process of identifying vulnerabilities, generating security assertions, and enforcing prediction policies. So it's designed to help secure the SOCs. So now let's walk through what Divas actually does. So Divas is an automated security framework that uses LLMs. First, it analyzes the SOC design. User provides the SOC architecture in a JSON format. Things like IP names, memory regions, bus configurations are in there. So the Divas uses LLMs to understand these structures and identify the vulnerabilities and maps them to CWE IDs. So what are these CWEs are? These are common weakness enumerations. These are a standard catalog of hardware and software weaknesses. So, for example, let's say we have a networking SOC and a third-party Ethernet IP accidentally or maliciously accesses a secure configuration register. So that register might hold settings that control encryptions. If the Ethernet IP disables encryption through that access, you have got an CWE 284 violation. So which is basically an access control issue. So usually these CWEs are mapped so that in the later stages of the framework we could generate assertions and move on further with the stages. So next, the generation of SVS comes into picture. So these assertions are used in simulations or formal tools to check if the SOC design is actually violating any of those security rules. And finally, if any issues are detected, the framework translates the verified assertion into actual RTL level security policies using a tool named Dispel. So this step injects logic into the RTL to block insecure behavior like stopping untrusted IPs from accessing protected memories. So let us look at a practical example in the next slide. So here, if we imagine a high performance automotive SOC, like what you would find in an autonomous vehicle, it contains multiple IPs, GPU, a radar controller, secure boot module. These all share a common AXI bus. Now, here is the risk. If the radar IP is a third party component and the secure boot module stores sensitive private keys, there is a possibility that the radar IP might unintentionally access those keys during a bus transaction. So this is a textbook case of CWE 522 insufficiently protected credentials. So manually auditing the HDL to check signal accesses and privilege levels, like whether the ports is set correctly, is time consuming and difficult to scale. So here comes the framework. So it solves it with automation. So first it reads a specification JSON file that detects IP names, address ranges, and bus configurations. And based on this, the framework uses the LLM to identify that key materials is being shared and flags like CWE 522 as a possible threat. So then it goes to the step further. It automates the assertions. For instance, we have given an example here, a property which is triggered on the rising edge of the clock. It checks whether the right address from the radar IP falls into the predefined secure address range, and the exclamatory sign ensures that access must not occur, and if it does, the assertion fail, flagging a security violation during simulation. Now the framework does not stop here in the detection part. It translates the assertion into actual RTL logic using a tool called dispel. So next we will see a visual representation in this slide. So here the block we are looking at is a model SoC where multiple components, a processor, a crypto IP, a DSP IP, and an untrusted IP are all connected in a shared bus. So this reflects a common architecture in a real world SoC. Notice that the crypto IP at the bottom left, it stores a private key, plain text, or generates ciphertext. So this key is highly sensitive and need to be tightly protected. Now let us look at the untrusted IP in the center. This could be the third party component integrated into the SoC. According to the zero trust model, we must assume it could behave maliciously, and in this case it does. The green arrow shows in this picture legitimate data flows from the crypto IP to the trusted component like the processors, and the red arrows shows an unauthorized read attempt. The unsecured IP tries to access the protected memory region where the sensitive key data is stored. So this figure is a perfect example why traditional SoC designs where everything on the bus is assumed to be safe are no longer viable, and we need to actively detect and prevent these access attempts, and that's exactly where this framework is. That's exactly why this framework is proposed. So now that we have identified the potential vulnerabilities and generated assertions, it's time to enforce production, and it is where the security policies comes into play. A security policy is nothing but a set of rules that define what kind of access is allowed and what is not allowed across different components. These rules are meant to protect the confidentiality, integrity, availability, or in short form, it's known as CIA of the SOC's asset. So now rather than manually writing these policies into RTL, the framework which is proposed by the author uses an automated tool called Dispel. It takes the security assertions we talked about earlier and translates them into synthesizable RTL logic. So here is a code snippet which is shown here. This code snippet checks if the crypto IP is performing a write to a protected memory region, specifically within the range given here. So if that condition is true, the policy immediately nullifies any write data from the SPA IP, which is given in the last line, like SPA dot write data is equal to 0. So why is this done is because the SPI IP is considered as an untrusted IP in this context. It's a potential threat. So this policy essentially cuts off the data flow where sensitive regions are being accessed, making sure no sensitive information leaks through insecure paths. So with the framework and the tool Dispel, these policies are automatically synthesized into RTL, removing the need for manual implementation. So now let's look at the existing current approaches. So the first one would be manual HTL analysis is one of them, where an expert goes through the RTL trying to spot potential vulnerabilities by eyes. This method is not scalable and even experienced engineers can miss edge cases. Then we have the automated techniques, things like static analysis tools, template based repair engines, and even some early applications of LLMs. But the issue with these methods is that they mostly look for functional bugs and not for security flaws. So if we consider an example over here for better understanding, imagine a third-party Ethernet IP in the networking SoC. If that IP manages to disable VPN encryption by modifying a secure register, it's a case of CWE 732, which refers to incorrect permission assignment. A static analysis a tool which catch a bug inside the Ethernet IP, but it would not catch the fact that the IP is violating a system level policy, like writing to a protected memory region. It should not access. So this example would highlight us the gap that the current tools focus too much on the local IP correctness and not enough on the global security enforcement. So this serves as an concrete example that these kind of frameworks are should be very much encouraged for SOC security, addressing the security SOC security related issues. So now comes our author's proposed framework. This is split into four major stages as per the author, wherein the first stage is the query generation, and the next is CWE mapping and filtering, and the next is verification, and then security policy enforcement. Let's look at each of these stages and understand how the flow goes. So the first and the foremost would be the design specification and query generation. So in this step, the user, usually a design engineer, provides high level information about the SOC using a survey style template. This includes details like what IPs are present, which ones are trusted and untrusted, and the range of memory blocks and the type of interconnects, say like AHB or AXI bus. All of this is then automatically formulated into a JSON file. For example, the user might specify the Wi-Fi IP is untrusted, flash is mapped from 1000 to 2000, and it uses an AHB bus. We could see a JSON response for this later in the slide. So now, if we move to the query generation, the framework passes this JSON file to and understands the structure of the SOC and the IP, which has the IP, the privilege levels, the memory regions. From that, it automatically generates a natural language style queries that looks for possible vulnerabilities. So one such query might be is given as an example: can the Wi-Fi IP access memory in range of 1000 to 2000? So the power here is that the system does not rely on raw hardware signals at this point. Instead, it speaks to the design intent, just like human security auditor would. Then it forwards those queries to the LLM like ChatGPT or Word, um, and then it processes it. So let me walk through an concrete example over here. So imagine a smart thermostat SOC. So the user input says the Wi-Fi IP is untrusted, flash memory lies between 1000 and 2000. So the framework generate queries like we mentioned above, and the LLM receives this and identifies this may be a violation of CWE 284, which deals with improper access control. So, and this is how the process looks like when it is automated, and there is no manual transaction over here. And that's why this step is very efficient and powerful. So here is an sample JSON response. So here we have the Wi-Fi IP, the flash memory. The Wi-Fi IP marked as trusted false, that immediately tells us it's untrusted, meaning it should not have access to critical regions. And the flash memory block, which within an address range of 1000 and 2000, and it is flagged as secure true, indicating that this region contains sensitive data. So finally, we have the bus AHP entry, which says the SOC uses the AHP interconnects to link its IPs. Now this JSON file is parses, and based on the zero trust model, it the IP is okay. Sorry, based on the zero trust assumptions that the untrusted IPs are always potentially dangerous, and it generates queries like can the Wi-Fi IP read from the address range 1000 to 2000. So this is a key moment because this question reflects a potential vulnerability which may be found, which is here is CWE to 84. The reason this query matters so much is because if the untrusted IP like a Wi-Fi module can read the flash memory, it could be potentially riskier. So here is where the algorithm kicks in. So in the next stage, what is the next stage is the CWE mapping is done using the LLMs, and a technique known as filtering is introduced. So these queries are mapped to a CWE, and why do we need a technique known as filtering, which we would see later. So how it works is the LLM interprets the queries, and SOC match them with a CWE database. So here we have given a lot of CWE's database which is present in the database. The author used this database in his experiments. So if we take an example for here, the CWE 522, which stands for insufficiently protected credentials, this CWE is triggered when sensitive credentials like encryption keys are exposed on a bus without proper protection. So next, yeah, now we are up to the point that why do we need filtering here? So we need filtering because the LLMs are quite powerful and their responses can include CWE entries that do not apply to hardware level SOC context. For example, they might list some irrelevant software based CWEs. So in order to filter all these outs, we just use a technique known as filtering, and the algorithm for that would be later discussed with my teammate, and he would be explaining that algorithm. So let me walk through the notation here briefly, and here the SOC configuration is represented, which is a set of all IP blocks in the system, each defined by its name, operation type, and address range. The database contains a detailed description of each CWE, like whether it's bus level violation, asynchronous or asynchronous. So the LLM produces a set of CWE prediction, and the filtering process reduces this to a much smaller and relevant subset. So let us make this filtering a concept with to understand it better. Let's go through an example. So we say have a query like, can the Ethernet IP write to a security configuration register? So here the LLM might respond with two CWEs 732 and CWE 284. But so this filtering technique is needed to prioritize which aligns more with the vulnerability, and here it would be an 284. So now let's look at the algorithm for it, and my teammate Karthigeyan Muralidharan will continue from here. Thank you.
So hi guys, this is Karthigeyan Muralidharan, and now I'll be explaining the algorithm for filtering the CWEs and mapping the CWEs. So for filtering the CWEs, the input is a list of CWEs from LLM responses denoted by omega uppercase, and the output is a filtered list of CWEs denoted by omega lowercase, and the data is an extensive DB denoted by lambda. So the basic process of this algorithm is, for each CWE in omega uppercase, if its ID matches an entry in lambda, it fetches details like bus, IP and type and passes it to algorithm 2 to add it to omega lowercase. If no exact match occurs, it computes the cosine similarity between the CWE's description and lambda entries, and with similarities greater than 0.75, it updates the CWE's ID to the matching lambda entry and then passes it to algorithm 2. If no match occurs, we query the AI, and if the AI confirms relevance, we add the CWE to lambda and pass it to algorithm 2. Otherwise, we discard it. Last, we return the filtered list omega lowercase. Then for the second algorithm, which is mapping CWEs, this function maps a filtered CWE to specific parts of the SOC, ensuring it's relevant before adding it to omega lowercase. So the basic process of this algorithm is, if the CW affects the bus and if it's not an omega lowercase, we add it. If the CW affects a specific IP, we check if the SOC has that IP by name and the IP's operation matches the CW's type. If yes and not an omega lowercase, we add it. Then if the if the CWE's IP type matches the SOC's IP operation, we add it to omega if not already present. Then we return the updated omega lowercase. Then next we will see the security assertion creation and verification, which is the third stage of the proposed framework. Now, normally we have to write assertions manually, but what this Divas framework does is it uses LLMs like ChatGPT and BART to write assertions. Now, if you look at the top part of the slide, you will see two example templates. On the left, ChatGPT generates a clean and reusable Verilog module with a property block and an assert statement. This is the format which was adopted in the paper. On the right, BARD uses a UVM style class based template which is less consistent and less extensible across RTL designs. So, this was not adopted in the paper. Also, below you can see a table that shows real examples of CWEs and the assertions created to detect them. For instance, for CWB 125, which is an out of bounds read, the assertion checks if a read address goes beyond the defined valid range, and if it does, it flags a violation. For CWB 327, which relates to insecure cryptographic key usage, the assertion ensures that a hard coded or default key is never used during operation. Now, next, we'll see about the translation to security policy and policy enforcement using RTLs, and this is the final stage of the proposed framework. Now, we begin with something like the user specs.json, which includes a condition, for example, a write address between a valid range, and an action such as forcing the write data to 0. This tells that if a certain IP tries to write to a protected address, it should be blocked. Next, we have an assertion in system Verilog that checks for this exact condition. This assertion gets triggered when the address range is violated, and it's useful for catching the issue during simulation, but it doesn't prevent the behavior. That's where the middle part comes in, the security policy spec.json file. This file is auto-generated from the assertion, and it has a predicate, a timing field, and the enforcement action. So this means that if a slave tries to read to this protected address range, we force the data to 0, essentially blocking the attack. Finally, this JSON policy is translated into actual RTL code as shown in the rightmost block that can be seen in the security policy top.sv. Now let us look at what algorithm 3 does. So this algorithm takes a set of assertions as input and produces a set of security policies as output. So the result is basically a policy that mirrors the assertion but is fully synthesizable RTL. So it can be used to harden the chip against real-time violations. Now next we'll go on to see the experimental results. Now we'll start with the evaluation benchmarks and setup. Now the authors use the MIT CEP SoC benchmark, which includes an OpenRISC CPU acting as a master and multiple other IPs like crypto, DSP and IO, and some of which are marked as untrusted. The SoC communicates over an AXI4 bus, which is a standard interconnect in industry designs. They also validated the security policies using two backends. One is simulation using Synopsys VCS to check assertion violations at runtime. The next one is synthesis using design compiler, where they implemented the generated RTL logic on 250 nanometer technology. Now let us look at how the LLMs outperformed. So ChatGPT outperformed BARD in generating relevant CWE matches. BARD sometimes included too many software-centric CWEs which were filtered out later. A few key CWE examples that emerged were CWE 284, which is improper access control, and CWE 522, which is insufficiently protected credentials. Then when it came to assertion generation, again ChatGPT did a better job than BARD. It generated more accurate SVA templates. However, some assertions still had syntax issues. For examples, using if and only if conditions in the wrong order or missing disable clauses. This could cause simulation errors. Despite this, the generated assertions were strong enough to detect important issues like out of bound memory access and key leakage. And these were verified in simulation using Synopsys VCS. So overall, the experiment demonstrated that Divas is capable of taking a high-level SOC description, identifying vulnerabilities, and automatically enforcing security at the RTL level. Now, next we'll see about the RTL policy enforcement and overhead. Now, here, once the SVAs are verified, they are converted into what's called as a three-tuple policy. So here, the first one is a predicate to detect violations. The second one is a timing condition to control when to check. And the last one is an action that enforces protection, like nullifying data or blocking access. These policies are passed to the Dispel tool, which synthesizes them into hardware. Now, what's great is that this insertion of security logic adds only minimal overhead. Now, if we take a look at the benchmarks for AES, the area has increased by only 0.19%, while the delay actually improved by 3.5%. This is likely due to timing changes in logic pipelining. For SHA 256, there is a 2.7% area increase and a 4.4% delay increase. Power consumption varied between plus 10% and minus 6% depending on the logic paths affected. Now next we look at some limitations of Divas. First, there are some LLM related issues. ChatGPT and Bard, that is, they both hallucinate, that is, they generate assertions or CWE mappings that are syntactically wrong or irrelevant. They also don't fully understand SOC level hardware semantics, which are out of the box. Secondly, even though filtering is partially automated, some manual tuning is still required, especially when new CWE types are encountered or context is ambiguous. Another limitation is that the framework has only been tested in simulation and synthesis. There is no hardware in the loop validation yet. So how it performs in silicon under real world workloads is still an open question. Divas has also only been evaluated on AXI based SOCs. There is no discussion about more complex interconnects like NOC, which is network on chip, which are common in large multi-core systems. So while Divas shows great promise in improving security automation, there is still room for it to grow. Now let's look at our analysis. That is, what were the key takeaways that we found from this paper. So at its core, this work proposes a complete end-to-end SOC security pipeline built on top of large language models. That's actually a major contribution because until now, most LLM applications and hardware were limited to documentation or small bug fixes. And Divas actually uses LLMs for critical design tasks, understanding architecture, generating vulnerability checks, and enforcing protections. It shows how LLMs can interpret natural language SOC descriptions, extract security vulnerabilities, and generate system verilog assertions that are not only used for simulation but also get converted into RTL logic using tools like Dispel. Now, this proves that LLM driven low overhead RTL enforcement is feasible in practical SOC designs. Now, as we saw before, this framework is fully pipelined from specification to synthesis and includes a curated CWE database, semantic filtering, and evaluation on a real benchmark, which was the MIT CEP SOC benchmark that was used by the authors. They even designed a filtering algorithm that applies semantic similarity scoring, which helps identify CWE matches even when the LLM returns ambiguous or fuzzy results. But despite these strengths, the paper is honest about its limitations. That is, there is a heavy reliance on LLM, which introduces some instability, like things like hallucinated CWIDs or syntax errors generated in SPS. The filtering step, while intelligent, still needs some manual curation. And more importantly, the framework hasn't yet been validated in actual hardware. It's been tested only through simulation and synthesis. Finally, the Divas has only been evaluated on AXI based SOCs. There is no support yet for large NOC based systems, which are increasingly common in high performance SOCs. Now, last, uh, let us see why we consider this paper as important. Now, like, we consider this important because this bridges the gap between AI reasoning and hardware verification, and it enables security policy enforcement without the need for any manual coding, reducing the workload. It introduces a new role for LLMs in hardware security automation, and it also sets the foundation of AI guided EDA flows. Now let's see what has been the impact so far. So its impact so far is it's inspired new work on LLM and also formal verification hybrid tools, and it has promoted the use of assertions and SVAs in security enforcements. It has also provided a reproducible methodology using open source benchmarks, and it also highlighted the need for domain specific LLM tuning.